Right, so polynomial functions are functions that have exponents, which are whole numbers, so basically 0 and up. We've talked about that before. Now, when written in standard form, okay, the exponents are lined up in decreasing order. So basically, it's the same order that you line them up in for your synthetic division and your long division and stuff. That's in standard form. Now, when you do that, the first term then is the term with the highest exponent, right? We call that the leading term. And the coefficient of that first term is called the leading coefficient. All right? And the degree is just the greatest degree of that first term. All right. So when I have an equation, so suppose I have an equation that looks like this. F of x is equal to 12x to the power of 0. Now that's a polynomial equation because it's got an exponent of a whole number, 0. But what's x to the 0? 12. So really that's just 12. Now that in itself, f of x equals 12, is a polynomial function. And because the degree is 0, the highest exponent, the degree is 0, we call it a constant function. And the degree is 0. All right. Now, when the exponent of the variable is a 1, and when that's the highest exponent of the polynomial, we call it a linear polynomial. When the highest exponent is a 2, it's a quadratic. If it's a 3, it's a cubic, right? And then higher exponents, right? So x to the 4, we call it quartic, and then quintic. But in general, this is what it looks like. So we have a, and then x to the n, blah, 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 blah. Okay? All right. Yeah. So, all right. Once you take that term with the highest exponent, the coefficient of that term is called the leading coefficient. And you can see here in the quadratic equation, for example, the leading coefficient is 5 and so on. Okay, so take a look at this example. What is the degree in this polynomial? 6. And the leading coefficient? 5, right? And if they were written such that it was not in standard form, you just put it in the right order. All right, we've done stuff like this before. We want to find f of 3b. So I have f of x, and now I want to find f of 3b. Well, what's happened here? The x switched to a 3b. So in the equation, anywhere I see an x, I have to switch it out for 3b. So this is going to be 3b squared minus 2 times 3b plus 5, right? So what is that?
9b squared minus 16 plus 5.
Right. And this is f of 3b. Okay, so take a look at this. I have two things happening here. It's 2 times f of 3x minus 5.
Oh,
so
it just says the front.
Oh, wait a minute. So, okay. Sorry, so it's like this, f of 3x minus 5, right? Okay, even better. So it's 2 times, now I have f of 3x. So let's see what f of 3x is, right? We're going to plug 3x in there. So we get 2 times 3x squared minus 3x plus 1. Is that right? And what else? Minus 5. Okay? So f of x is 2x squared minus x plus 1. And it's 2 times f of 3x minus 5. Okay. Let's simplify this. So it's 2 times, Here I get 2 times 9x squared, which is 18x squared, minus 3x plus 1, minus 5. And if I distribute the 2, 36x squared minus 6x plus 2 minus 5. And then I simplify all the way. Okay? Yes. This next one is a little bit more involved. I have two things at play here. First, I have b of 2x minus 1. So I'm going to try to color code this. Let's just do b of 2x minus 1. Okay? b of x is this. So let's find b of 2x minus 1. Okay? All right. So 2 times 2x minus 1 squared plus what? 2x minus 1 minus 1. Did I do that correctly? Okay, now, all right, let's see. This is 2 times, and if I square this, what will I get? 4x squared, almost, minus 4x plus 1. All right, plus, what do I get here? 2x minus 2. Everybody with me so far? Okay, now, here we get 8x squared minus 8x plus 2 plus 2x minus 2. So this is 8x squared minus 6x, and that's it, right? Okay? Now, what else do I have here? I have a minus and then a 3bx. So now let's do the 3bx. So this is 3 times what? Right? Plus x plus minus 1. So 3bx is how much? Positive 6x squared. I'm leaving the negative out for a minute. Positive 6x squared plus x, 3x, minus 1. Okay, so here, let me just copy down what it is that we're being asked for. Is this what we were being asked for? Right? Okay, now, I found b of 2x minus 1. And what did I find that to be? 8x squared minus 6x. Now, minus, and I found 3bx to be what? 6x squared plus 3x minus 1. Okay? Now, can we simplify this? Ooh, minus 3. Way to go. All right. Okay, and then, so it'll be 2x squared minus 9x plus 3. After all of that. All right, so talking about graphs of polynomial functions. The constant function, which we said had a degree of 0, right, is just a horizontal line through y. So for example, if you have f of x equals 5, that's the same as y equals 5, and it just crosses through y equals 5. Linear function, where there is a degree of 1, this is like any of your mx plus b equations, right? You get a diagonal line. Now, quadratic function, that's something that you guys are experts on after chapter 4. you get your parabolas, and it either faces up or down. Okay, so here is what the cubic function looks like. And if you notice, so this has a degree of 3, right? So this is what it looks like. And here there is a degree of 4. This is the chordic function with a degree of 4, all right? So what I want you to do for a minute is take a minute and compare the degree of 3 with the degree of 4, all right? And not really compare, but maybe contrast. Let's try to see some of the areas, or one particular area that I'm looking for where they are not the same. So with a degree of 3, okay, where the degree is odd, 1, 3, 5, 7, 9, if you look at the very ends of the graph, right, the very ends of the arms of the graph, one side of the graph goes up and the other side goes down. However, if the degree is even, so something to the power of 2, 4, 6, 8, both ends will be going up here. In the case of the quadratic function with a degree of 2, both ends will be going down. So when the degree is odd, okay, one end is going up, the other is going down. When the degree is even, they're either both going up or both going down. Okay, very, very important. That will never change, ever. Okay? Now, as far as the other similarities, all extremely, extremely good points. The degree of 4, you see it's symmetric around the y-axis. So if you cut this down along the y-axis and just basically fold it over, the left and right ends match perfectly. And later on, this is going to match into our even graph and our odd function and so on and so forth. Okay? So, also, the degree tells you the number of possible solutions to an equation, right? If the degree is 1, it's only possible for it to cross the x-axis once. So one solution. If the degree is 2, the maximum it could touch the x-axis is 2. If the degree is 4, the maximum it could touch the x-axis is 4. So 4 solutions. All right? Yeah. Brings us to end behavior. And end behavior is exactly what it sounds like. It's the behavior in the end of the graph. All right? Now, we talked about what is the domain for all quadratic functions? All real numbers. And it's the same for all polynomial functions. It's all real numbers, because you're always going to have a nice, smooth-looking, roller coaster-looking graph. Okay? Now, the end behavior is what happens as x approaches infinitely large numbers. Like, what happens as x approaches positive infinity or negative infinity? All right? So let's take a look at this one here, the cubic function. So let's take a look at this one, the cubic function. Now, suppose my volunteer here, I have a volunteer, his name is Mr. Polynomial. And suppose Mr. Polynomial is here, and he's walking along the x-axis. Okay, he's walking along the x-axis. Now, normally, we're always just concerned with the x values, like x equals 0, 5, oh my god, and then when we have like x equals 10, it's oh my god, like such a huge number. Let's get away from all that. Let's say he walks towards x equals 100. He passes that. He goes to x equals 1,000,000. Passes that. X equals 1,000,000,000. X equals 1,000,000,000. And he gets closer and closer to x equals infinity. Okay? And the entire time as he's walking towards x equals infinity, he's looking at the graph. So as he's moving along, he sees that the graph is also moving, right? Either up or down. As he's moving along to the right here, is the graph gradually moving up or down? Up. So as x approaches positive infinity, f of x is the graph. Is f of x going up or down? Up. So we say f of x is also approaching positive infinity. All right? So we say as x approaches infinity, f of x approaches infinity. Now, what if he's now going to the other direction? So as x approaches negative infinity, as now he's going over to, negative a trillion, where does he see the graph going, up or down? Down. So f of x approaches negative infinity. Okay? And when we say end behavior, this is what we're talking about. All of that. Okay? So let's just analyze a few things here. Okay? Suppose you have a function, the degree of which is even, right? Remember how we said both ends go up or both ends go down? All right, now, suppose the leading coefficient is positive. So I have, for example, 2x squared, okay? Or I have 4x or 6x to the 4. Or I have positive x to the 6, and so on and so forth, all right? Both ends of the graph will be going up, okay? However, if I now have an x squared, an even degree, but a negative coefficient, or like negative x to the 4, both ends will be going down. You see what I mean? Okay, so negative. Suppose you have an odd degree. So suppose you have 2x to the 3. All right, on the right side, it goes up, and on the left side, it goes down. So as x approaches negative infinity, f of x approaches negative infinity, and so on and so forth.
Does it matter whether the leading coefficient even or odd?
No, it matters if the leading coefficient is positive or negative.
They do also do f of x approaches positive infinity.
Right, as x approaches positive infinity, f of x approaches positive infinity. All right, let's take a look at this example. Okay? It says, first of all, is the function an odd or an even degree? Odd. What is the degree? 3. How many real zeros are there? 1, because it only crosses the x-axis once. Estimate the real zero. Right, so it's somewhere between -2 and -3, right? This is where my science background with like sig figs and accuracy and precision comes around. The most precise you can be here is 0.5, because we don't have enough calibrations to go to like 0.3 or 0.2. So just go to -2.5 and you're good. So x is about -2.5. Now to describe end behavior. So what we do is this. As x approaches positive infinity, f of x approaches something, and we're going to fill that in. And then as x approaches negative infinity, f of x approaches something, and we're going to fill that in. So whenever you ask for end behavior, just write down this template, and then all that remains, the solution, is this. All right, so as x approaches positive infinity, as I'm walking towards positive infinity, where do I see the graph going, up or down? If it goes up, then it's what? Positive infinity. And as x approaches negative infinity, where do I see the graph going? Down to negative infinity. Okay? And that's just amazing. So, here's a little secret for the degree. Okay? How many times does it turn around? it turns around twice, right? So look, here it turns around one time here and one time there. You look at the number of times it turns around and add 1. Huh? Yeah. Number and then plus 1 is the degree.
Also,